In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself, Pranav, is here to deliver today's presentation, Power Transformer, Part 17. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with sandwich winding. Sandwich windings are most commonly used for transformers of shell-type core construction. Shell-type transformers are basically employed for the configuration of high ratings and low voltage system. The coils, which are to be constructed with flat conductors wound around a rectangular form and as arranged to make the conductors into discs. So the coils are referred to as sandwiched or pancake coils. The HV and LV windings, both to be made split into a number of sections where each section of HV winding lies between two LV winding sections. Such type of alternate disc formation are then made to have spiral from outside towards the center in an interleaved arrangement with individual coils being stacked together and isolated each of them by insulating materials such as electrical grade paper or kraft paper. By subdividing the LV and HV winding into a large number of sections or coils and arranging alternatively the HV and LV coils close on the same magnetic axis near the yoke has therefore made to increase the mutual flux and permit easy control over the short circuit impedance of the transformer and leakage reactance. Only by increasing the numbers of sandwiched coils, the reactance can have to be substantially reduced. In designing transformers capable of handling very high currents, so it is obvious that in every respect, the coil assembly would have to undergo high forces as because of high current levels. Forces as produced within the coil assembly may tend to cause relative movement between adjacent components thereof, resulting excessive wear and tear of electrical insulation in critical places. While in high current operation, there may be a possibility of producing significant amount of heat, causing certain leakage and certain breakage of structural elements in the coil assembly, as well as failure of insulation therein. Hence, in a sandwich assembly, it is required to have a proper impedance matching while forming a coil, and the application of requisite insulating means must be secured together with the winding configuration so as to encounter the excessive heat. Sometimes a stainless steel water cooling tubes that has been embedded in the coil surface, and for better isolation, the coil itself is being encapsulated in a fiberglass or epoxy material or synthetic resin bonded paper tube. See the diagram of the sandwich winding. physically stacked sandwich or pancake windings. Now, optimization of transformer winding, heat transfer criteria. Most of the power transformers are operating at efficiency 95 to 98.5% or even more, which means the corresponding power loss percentage is very minimum. Though the power loss percentage is found to be small, but the amount of heat as generated appears to be very large in absolute terms and ultimately turns out to be the critical factor for safe and economical operation. Power losses in the core due to the hysteresis of the ferromagnetic material or due to eddy currents which tend to resist flux alternation. Power losses in conductors due to I square R losses from main windings, eddy currents induced by leakage fluxes. Therefore, what I am telling, power losses in the core, it is due to the hysteresis of the ferromagnetic material and due to eddy currents which tend to resist flux alternation. And power losses in conductors due to I square R losses for main windings and eddy currents induced by leakage fluxes. However, thermal consideration has become much pertinent while the hazard arises from localized heating in the conductor insulation. Then the hotspot temperature criteria sometimes may lead to catastrophic failure by damaging the craft paper insulation of conductors. The total core and winding arrangement as immersed in oil. So, oil temperature at above 140 degrees centigrade, there would have been a chance of evolving gas from oil, and that may instigate to trip the affected transformer. Truly speaking, the life of the transformer is adjudged by the life of the conductor insulation rather, where the aging rate of the insulation is basically regulated by the rise of temperature. Now the points are very important, you see. It is technically accepted as a rule that every rise of temperature approximately of 6 degrees centigrade may lead to have doubled the rate of using life of the transformer. Another one, aging starts occurring at its normal rate while the operating temperature of the transformer is at the range of 98 degrees centigrade. In shell type construction, the winding is configured with flat, sandwiched or pancake coils. However, in coat type transformer arrangement, while for the layer winding, the coils may be wound axially in concentric cylindrical cells, and the coils would have been radially wound in case of parallel discs of making the disc winding. For power transformers of both the construction, winding configurations are there to be completely oil immersed. Now, transformer oils are of mineral electrical insulating oils processed from fractional distillation and treatment of crude petroleum. Oil in transformer serves the purpose. One, oil provides the liquid insulation in between the windings and other conductive parts of the transformer. Number 2, acts as a cooling medium. Number 3, oil is to protect from interaction of atmospheric oxygen and the cellulose made paper insulation, kraft paper of the winding. Properties required to fulfill oil all these criteria, that is, to serve as a cooling medium so as to transmit the heat generated in the coils and core into outer walls to dissipate it, and also acts as a liquid electric insulator. 1, requires excellent dielectric strength, that is more than 28 kV RMS, resulting in minimum power loss. Number 2, mostly devoid of moisture content as it affects the dielectric properties of oil and also affects the paper insulation of the core and winding. Number 3, high resistivity leading to better insulation values between windings. Number 4, high thermal conductivity and thermal stability facilitating reduction in evaporation losses. Number 5, excellent aging characteristics even under severe electrical stress. Number 6, virtually free from corrosive sulfur, leading to enhanced chemical stability and protection against corrosion. Number 7, wider operating temperature range resulting from higher flash point, that is 140 degrees centigrade or even higher, and lower pour point, that is minus 40 degrees centigrade or lower. Evaluation of variable factors on transformer performance. There are various factors that affect performance parameters, and thereby life expectancy of the transformers would have to be deteriorated. Main design parameters are there to be evaluated with the underneath factors. 1, no load loss, short circuit impedance. Though power transformers efficiency is typically 99.5% or more, but as an energy converter, transformer has obviously to dissipate losses depending on operating characteristics as well as system parameters. Transformer losses are to be influenced mainly by the current as flowing in the coils and also due to the alternating magnetic field in the core. The losses associated with the coils are termed as the load losses, while the losses produced in the core are called no load losses. Again, I repeat, the losses associated with the coils are termed as load losses, while the losses produced in the core are called no load losses. However, low loss rather than low cost designs are readily be acceptable in modern system network. 1, no load loss on performance parameters. No load losses, which practically occur in an unloaded transformer as due to the power dissipated in the magnetic core subjected to a time varying magnetizing force. No load energy losses are thus to be equal the amount of power required to keep the iron core of the transformer magnetized. These losses are the iron losses, which are the sum of the hysteresis loss and eddy current loss. No load losses depend on the applied voltage, frequency, and proportional to the core material with the lamination thickness and mass of the core. The no load loss of the transformer, which is rather unaffected by the load, remains constant for a given applied voltage and be continuous during the period the transformer is connected to the supply. Important point to be noted, because most transformers are energized at all times. So, continuous and constant generation of no load losses have therefore be the high cost evaluation and therefore it is highly desirable that the no load loss should be kept to a minimum value. Now see the contributing components of no load losses. One is hysteresis losses in the core laminations, eddy current losses in the core laminations, I2R losses due to no load current, stray eddy current losses in core clamps, bolts, and other core components, and dielectric losses. Now, hysteresis loss and eddy current losses in the core laminations, these two losses would have to contribute over 99% of the no load losses. As of the smaller thickness of the laminated sheet of electrical steel, so its eddy current loss is far less than the hysteresis loss. Now, I2R losses due to no load current, stray eddy current losses in core clamps, bolts, and other core components, and dielectric losses. These three losses in combination, stray loss is related to leakage flux and eddy currents. This is for stray loss is related to leakage flux and eddy currents. Contributions of all are comparatively very negligible. Hysteresis energy loss. According to Steinmetz method, the hysteresis loss per cubic meter per cycle of magnetization of magnetic material mainly depends upon one, maximum value of flux density, the magnetic quality of the material, then hysteresis energy loss is directly proportional to B to the power 1.6 joules per meter cube per cycle. Hysteresis energy loss pH is equal to eta B max 1.6 frequency F V joules per second or watts, where eta is a constant for given specimen and a range of flux density and is known as Steinmetz constant. Bmax, peak value of the flux density in the magnetic material. F is the frequency of reversals of magnetization in hertz. V is the volume of the magnetic material in cubic meter. Hysteresis loss can be minimized by using core material with high value of permeability, as that has created the least hysteresis loop area for the core. If I restrict the hysteresis loop area automatically hysteresis loss will be minimized. Hysteresis loss is the prime contributor to no load losses and has to originate from the molecular magnetic domains in the cold laminations, which would resist to have the respective process of magnetized and demagnetized of the ferromagnetic core material by the alternating magnetic field. As because of the applied AC voltage, the magnetizing force which has to produce at the primary of a transformer would have to change its direction in each cycle. The magnetic domains in the cold laminations have also made to realign them in the direction of the magnetizing force as produced. To accomplish this realignment process of the magnetic domains, some energy is therefore to be required, which is obviously taken from the input power, and the remaining part of the input power is transferred to the secondary winding. The consumed energy is the loss, which has to vary with the selection of core materials and their corresponding magnetizing ability. Note, one of the most disadvantages of using CRGO coat steel is that any factor which requires the magnetic flux to deviate from the grain direction of the steel sheet will increase the core loss. Again, I repeat, one of the most disadvantages of using CRGO coat steel is that any factor which requires the magnetic flux to deviate from the grain direction of the steel sheet will increase the core loss. The hysteresis loss in a given magnetic material would have been made to minimize by decreasing the maximum flux density established through it. It is understood that for a given average flux density and frequency, the core loss is directly proportional to the conductivity and inversely proportional to the permeability. Thus, to minimize the core losses, cold laminations should have to be made from a ferromagnetic material that has high resistivity and high permeability. Hysteresis loss, which practically plays an important role, so for transformer core loss is concerned while operating at high as well as low frequencies. In fact, constantly occur no-load losses can accumulate to a considerable amount of energy and costs during the long technical lifetime of a transformer with no matter of load operating strategies. The energy and economic savings can be achieved through some design investigation of the consequences of minimizing the no-load losses for transformers. Eddy current losses in the core laminations. Eddy current loss in the core arises because of the induced EMF in the steel lamination sheets and the eddies of current formed due to these sheets. Since the eddy current loss depends upon the rate of change of flux as well as the resistance of the eddy current path, it is reasonable to expect the loss to vary as the square of both the maximum flux density and frequency. That is, number of complete magnetization cycle per second. Eddy current produces power loss, that is PE, in the lamination. That is P equals to KE B max square F square tau square V joules per second or watts. KE, eddy current coefficient, its value depends upon type of core material, Bmax, maximum flux density in Tesla or Weber per meter square. F is the number of complete magnetization cycle per second. Tau is the thickness of steel laminations in meter. V, volume of the magnetic material in cubic meter. The alternating magnetic flux, which is being constantly set up by the external sinusoidal supply voltage, has to influence an electromotive force in the bulk of the core laminations, causing a flow of circulating current. These flow of circulating currents are called as eddy currents and would have to depend inversely upon the resistivity of the core material and directly upon the thickness of the core. Corresponding losses per unit mass of core material thus vary with square of the flux density, frequency, and thickness of the core laminations. Eddy current losses within the core cannot be fully eliminated. However, losses would have been significantly decreased by constructing core from a material of higher permeability and less conductivity, which therefore commonly made from thin silicon steel laminations of having thickness 0.35 millimeter for power transformers. Exact selection of highly permeable material must have to ensure for achieving a very low reluctance path for the magnetic flux within the core. As and when ferromagnetic core begins to saturate, the heating due to eddy currents and hysteresis effect would have to start increasing rapidly. Important point, As and when ferromagnetic core begins to saturate, the heating due to eddy currents and hysteresis effect would have to start increasing rapidly. In the core manufacturing process, highly permeable materials such as CRGO steel that can provide very low reluctance path of magnetic flux, since the grain orientation of the silicon-based magnetic core must have to be made parallel to the flow through which magnetic fluxes flow, or otherwise core loss will be more. To restrict the eddy current from surging into transformer core, a very thin layer of insulating coating for providing so as to essentially isolated from each other of these thin silicon steel laminations. The purpose of this insulation is to prevent the circulation of eddy currents within the core. For the formation of core, these thin insulated laminations are assembled together to provide the required magnetic path with the minimum of magnetic losses. The resistivity of the CRGO steel sheet itself be high, thus eddy current loss would have been restricted by making the laminations very thin. Design approaches for reduction of transformer no load losses, that is to minimize the losses in core. Core material grade selection is critical, and each grade has an effect on efficiency on a per kg basis. Number 2, select core material of lower magnetic flux density. Number 3, increasing the core cross-sectional area. Number 4, core window height is to be reduced. Number 5, higher number of turns of HB winding. Now, core formation with amorphous metal and grain-oriented silicon steel. Selection of core material for transformer manufacturing purpose is a critical phenomena, and that has to be judged through emphasizing of transformer capacity, efficiency in power applications, sustainability, and cost involvement. Two types of materials are so far been commercially available for transformer core manufacturing process. Number 1, amorphous metal alloys. Another is CRGO core steel. But globally, most of the power and distribution transformer cores in service are of cold rolled grain oriented silicon steel, CRGO laminations. The performance of transformer is really affected due to presence of distortion in the input supply voltage and nonlinearity in the load current. When transformer is lightly loaded, the coal loss would have become the largest loss component of a transformer's total losses. Core material selection should have to be made with the following criteria. A, thickness of the lamination. B, mass of the core. C, resistivity. D, density of the core material. E, coefficient of hysteresis losses. And F, value of Steinmetz constant. Comparing all these parameters, that is these 6 parameters, which are leading to a demand for low coal loss and low magnetorestriction material for core manufacturing process, has ultimately find out a unique alloy named as amorphous metal. Amorphous metal alloys is the key composition of iron, boron, silicon alloy, having with a non-crystalline structure produced by ultra rapid quenching of molten alloy with the cooling rate of 10 to the power 5 to 10 to the power 6 Kelvin per second. 0 Kelvin is 273.15 degrees centigrade. The amorphous alloy is cast in extremely thin ribbons, that is of thickness 0.025 millimeter, to achieve the required magnetization properties, and is received in the form of ribbons. Amorphous alloy has then been exhibited a unique molecular arrangement that is random in structure rather than the organized crystalline structure of CRGO core steel. As of no crystalline grain boundaries to prevent motion of magnetic domain walls, amorphous metal, whose main ingredient is iron, exhibits excellent magnetic properties such as high permeability and low loss, while having a high saturation magnetic flux density. In 1986, type of liquid filled transformer using core material of amorphous metal was introduced commercially. Due to its unique molecular structure in which the metallic molecules exist in a random pattern, amorphous metal cores, while energized, are more readily magnetized and demagnetized, resulting in significantly lower energy loss compared to conventional CRGO steel cores. Amorphous metal core has some explicit criteria of having low field magnetization, for which hysteresis loss is there to be low, and because of high electrical resistivity, eddy current loss is also to be suppressed mode, also to be in suppressed mode. Constructing core by using amorphous metal alloys, it has been exhibited that the core losses are getting reduced almost by 70% with magnetizing current, as low as 55 to 60%. And overall temperature rise is much less as compared to conventional grain-oriented silicon steel core transformer of same kVA rating. Again, I repeat, constructing core by using amorphous metal alloys, it has been exhibited that the core losses are getting reduced almost by 70% with magnetizing current as low as 55 to 60%. And overall temperature rise is much less as compared to conventional grain-oriented silicon steel core transformer of same kVA rating. Iron, boron, silicon alloy, where mainly iron with small percentages of silicon and boron. Fe is about 78%, boron 13%, silicon 9%, is the best available amorphous alloy in the present market. Amorphous metal ribbon having thickness of 0.025 millimeter is therefore cut to length based on design requirements to develop C-core structure of square or rectangular in cross section. Formation of annular shape core packet is then to be made and placed in an oven for proper annealing. Special grade of glue is applied at the corner sides of the annealed core packet and cured in infrared oven so as to make the core packet much more rigid to accept the winding stress. Entire core manufacturing process should be channelized with precise controls and proper care while handling. Transformer core, while made from amorphous ribbon of having 10 times thinner laminations than that of the available thickness of conventional CRGO steel sheet, has thereby resulted of much lower eddy current losses. Distribution transformers, which are energized round the clock, have their operating performance always been affected due to presence of distortion in the input supply voltage and nonlinearity in the load current. So, distribution transformers are a significant source of energy loss in an electric power network, which consists of no load losses and load losses. No load losses are constant and continuous, so long as a transformer is in service, while load losses would have to vary with the square of the load current carried by the transformer and are only significant under higher load conditions, that is, at the peak time load demand, which is confined within 6 to 8 hours a day. Therefore, no load loss is much more dominant and needs to be reduced in all size of distribution transformer. By determining the economic trade-off between the price of the electric unit as supplied versus the cost of transformer losses, the preference must have to be made for using amorphous core transformer instead of conventional transformer of the same kVA rating. During 1980s, global power companies, especially those who were getting hugely burdened with high electricity generating cost, had continued to invest in energy saving measures. The Electric Power Research Institute, EPRI, of United States had identified the area of distribution transformers as a primary target for enhancing energy efficiency and also being intended for technical guidance as well as initial funding for further improvement in manufacturing process of transformers with amorphous core material. For the same kVA rating, the amorphous core transformer, although slightly heavier, but would have to operate with significantly lower core loss and exciting current, resulting in smaller temperature rise than conventional CRGO core transformers. Important points to be noted. Maximum saturation flux density of amorphous metal is almost 1.56 Tesla, whereas for CRGO steel, that saturates almost 1.9 Tesla or more. This has indicated that as of higher saturation flux density in case of CRGO core results in higher core losses, but in contrary, as the volume of core is relatively less, so less amount of copper winding is required, resulting an obvious reduction of copper losses. Thus, for the same kVA rating using CRGO core, the mean length of winding turn reduces. So, mass of copper in winding reduces. Therefore, cost of the transformer would have been reduced because of reduction in the cost of winding. As the saturation flux density of thinner laminations of amorphous metal ribbon core is less, so that would help to reduce core losses. But simultaneously, a larger volume of core is to be dealt with, resulting in longer turns of winding, which means involvement of higher resistance, resulting in more copper losses. Hence, it can therefore be concluded that the core losses as well as copper losses both would have been related upon the maximum saturation flux density of the material to be selected for constructing transformer core. Due to complicacy in manufacturing technique, the overall cost of amorphous core transformer is approximately 20 to 30% higher than that of the conventional CRGO core transformer. As the metal being very hard and therefore of some technical difficulties in constructing core using amorphous steel of thinner laminations have restricted the size and capacity of the transformer and available range at present not beyond 2500 kVA. However, severe technological improvisation are continuously evaluated in the process of transformer designing and manufacturing options which may have to allow amorphous metal to be used in transformer core manufacturing process in a manner similar to silicon's steel core transformer of expected units larger than 2500 kVA. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.